Welcome to today's video. Today we're going to start with integration in higher dimensions. First, I'll give you a little introduction and an overview of the different kinds of integrals that we will tackle in our following videos. And then we'll go deeper into more details into these specific kinds of integrals. So this is going to be section 15. Higher dimensional integration. And we'll start with 15.1, an introduction. So recall in functions on the real line, the purpose of integration was twofold. We motivated integration by the need to compute the area under a graph, and we later found out that integration is also the inversion of differentiation. So the integral provides an antiderivative. So those are basically the two main applications of integration for functions defined on the real line. Things are a little different, a little more complicated in higher dimensions. So we'll see several types of integrals there. But before I give you an overview of that, let's first make a note of what I just said. So for functions on R, integration serves mainly two purposes. The first one is computation of an area usually below a graph. And the second is as the inverse operation of differentiation. So this leads to the notion of antiderivatives. Now what about integrals in the multivariate case? Of course, we can also try to compute areas and volumes below the graphs of functions, so that is obviously an important application of integration in this multidimensional setting as well. So first possible application of integrals is the computation of areas and volumes. Right? And that plays a role for functions f defined on some r to the n or a subset of r to the n mapping to R. You can imagine a setting here easily. So let's say we have a function defined on R2. Like this is the x1 axis, this is the x2 axis, here is the x3 axis. If we define a function on those axes, for example, could use a grid like this. Look at the function values on these grid points here. And then let's say that looks somehow like this. Here's a lower function value, a higher value, a lower value once again. Let's make those higher, lower, And then we also need function values for all the other lines here. So let's say here's one more value, here's one, we got one value here, one right there, a little higher here. And then maybe we have a function that somehow looks like this. So here's the lines where the function intersects with the coordinate planes. Yeah, somehow similar to this setting here. Yeah, so maybe like that. And let's say here we have something like this. Yeah, so that might be the graph of a function f here. That's the graph of f. And then of course one can ask, what is the volume between that graph of f and the x1, x2 plane, for example? So volume between graph of f and x1, x2 plane. Okay, so that's one possible questions to ask. Of course, one could also restrict this a little. So for example, if we wanted to restrict our question to the volume over a certain area, like this. So this is an area here in the x1, x2 plane, and we just want the volume over that area. So volume over a certain area in x1, x2 plane. That loosely corresponds to intervals on the real line, but of course sets in the x1, x2 plane may be a lot richer in shape than for simple intervals. And we could also restrict the dimension somehow. So we could ask if we have a curve somewhere in either the x1, x2 plane or in space somewhere, then what about the integral along that curve? So for example, we could ask for the integration along this curve here, right? So that's a curve in x1, x2 plane. And we could ask, what about the integral along that curve? So here, how does that work here? So there's this point. There's a corresponding curve up there, and we want the surface of this area here. Okay, so we could ask for the surface enclosed between a curve in the x1, x2 plane and its image under f. Of course, you could ask similar questions as well. So you could ask for the integration along a curve more generally. Yeah, so instead of computing an n-dimensional volume, in this case a three-dimensional volume, you could restrict your function to a certain curve and ask, well, that's pretty much the same as a function that's defined along the real line. Could I just integrate along that curve? Okay, and if you want, that is somehow a generalization of one-dimensional integration. To the case of not just the simple real line, but bent versions of the real line. And of course, you can also have a look at curves in higher dimensions as well and ask about that. So what about integrating along a curve that is not in the x1, x2 plane, but that lives on that surface actually. So kind of what if I want to know how much energy I have to spend for a hike, for example. Yeah, then I need to figure out what is the energy that I spend along a certain way, along my graph, along my hills and mountains, and the ways the hiking path that I take. So I can model that by a curve. An integration along that curve of the function along that curve will give me the total energy spent during a hike. Okay, so for example, that might be important if you want to know something like the energy spent for a hike in the mountains. And along the same line, I could also just ask what is the length of that curve. So without overlaying a function, hills, something like that, I could also ask, what about the length of a curve? That also amounts to an integration that is to be done. Okay, so we can integrate over curves and of course also over surfaces or higher dimensional analoga. So let's just say over sub-dimensional surfaces. We don't have to necessarily compute fully dimensional volumes. We could also compute surfaces of a lower dimension. For example, two-dimensional surfaces embedded in 3D space. Or as another possibility, again, let's imagine we are moving somewhere in the x1, x2 plane along a curve. And now let's say there's wind. Then of course the energy that we need to spend for our movement is somehow related to the wind, right? If we're moving in the same direction that the wind blows, then it's easier. We don't need to spend that much energy. If we're moving against the wind, then things will get harder. We need more energy. So we need to have a way of taking this into account. And functions like that associate a motion with every point in the plane, those are called vector fields. We'll talk more about these in a later video. But think of that as another possible integration over vector fields. So that usually models something like movement in a force field. You have a field that somehow influences the energy that you need for your motion. So for example, the energy spent for a hike on a windy day, yeah, then that wind is like the force field, okay? And of course, one other thing that we have to take into account here, we have not talked about so far, is what about that second application, the inversion of differentiation? How is that possible in multi-dimensional integration? Is there something like that? And actually there is, but it's not that easy, that apparent anymore. Problem here is consider a function f from Rn to R, to the reals. Then the derivative of that function is basically the gradient. So the gradient of f, that's a vector in R to the n for each possible point x. Now you could say that gradient computation that defines a function. So the differential of f defines a function. And we call that function gradient, and we'll denote it by grad. right? So that's the function grad f, the gradient of f. That's a function that assigns to every point in Rn another point in Rn. And more specifically, it assigns to each x in Rn the gradient of f evaluated at point x. Yeah, you could say this derivative, this differential, is again a function, and we call that the gradient. Yeah, so that function assigns to each point x in Rn the value of nabla f of x. And that's something like the one-dimensional derivative function. So for functions of that kind, we can ask, is there a multivariate function such that this given function is the gradient of that? Okay, so for a given function small f, and that needs to be a function of a gradient-like kind, so it needs to map from Rn to Rn. We can ask something like, is there a function capital F that would then map from Rn to R such that the gradient of that function capital F is our given f. So in that sense, we could define an antiderivative in higher dimensions as well. But it's not that universal anymore. Yeah. For example, if we have a function that is not defined as Rn to Rn, but for example a function like this, then what would an antiderivative of that be? Yeah, this cannot be a gradient. So what does that even mean? An antiderivative of such a function? Maybe that's not possible at all. And it turns out we need a very special setting to define what an antiderivative is. So that's not as universal as it was in the one-dimensional case anymore. But there is an analogy, and we'll talk about that as well. Okay, so this concludes the introduction. In the following videos, we'll see more details of all of the points that I've just mentioned. And we'll start with volume integrals.